I guess I'll start again. Okay, so we've seen a couple of explicit examples of this wall crossing phenomenon. And so the problem of wall crossing now is, suppose that you know all of the invariants at some particular phi2, at one point, say. You want to determine them at any other point. Well, in particular, that more or less reduces to the question of, can you get across a single wall? So if you can get across one wall, you can just iterate to get across more. So how, just knowing these invariants omega, can I determine these? And that's what Maxime explained how to do in his talk, but in a more general setting. So let me just specialize it. Let me just specialize it to this case. Well, I'm afraid I'm really going to repeat a bit of what he said. So the formula involves something which at first looks really weird. I mean, it looks kind of alien to the geometry of this situation. So this is the Kontsevich-Seuvelin wall crossing formula. So we have to look at the way I described it. I hope this is the correct way of describing it. So let's consider. So we have. Let me remind you, we had gamma, which was the first homology of this covering curve. So just as in Maxime's talk, this is a local system over the parameter space. But locally, you can just think of a single lattice. And let's consider the group ring. It's called a group ring, right? Z of gamma. So I just want to consider formal linear combinations of elements in homology. So a typical element of here. Gamma plus 2 gamma prime or something. And the multiplication in this ring will be given by the addition in homology. So the slightly weird thing that if I have two homology classes, I'm going to write their product, what you would usually think of as their sum. It's naturally, if you think of them as being pans that you're somehow composing, and that's how it will naturally arise later. So think of it that way. And I want to let A. So let's let A be the field of fractions of that group ring. So I'm going to allow myself things like gamma plus 2 gamma prime divided by 3 gamma double prime plus 1 or something like that. So what Kontsevich and Seuvelin tell you to do, so they thought of this field as being like the field of functions on some torus, some auxiliary torus, which is C star to the rank of this lattice. And what they say is, that now for any gamma, think of this gamma, this one as being now the charge of some actual object, some special trajectory. So for any gamma, we'll define an automorphism. So let me call it K gamma. K gamma of this algebra A. So in Maxime's talk, these similar things appeared. They were called TAB. He was in some particular basis. So I'm calling these things K gamma. Well, what's it defined by? So I just have to tell you how it acts on these generators. So K gamma of gamma prime is just gamma prime again, but multiplied by something. And it's multiplied by basically 1 minus gamma to the intersection pairing of gamma and gamma prime. So this lattice comes with it, has this natural bilinear pairing, which is just the intersection pairing on the homology of sigma. And so here's an automorphism, just multiplies every gamma prime by this. This is really an automorphism because this thing is linear in gamma prime. Okay, I cheated a little bit, so there's a tricky sign in this business, which I would not like to talk too much about, but honesty compels me to write it. So it's not quite 1 minus gamma. In the conventions that I'm in, I have to throw in a little sign, sigma gamma, which is plus or minus 1. So in Maxime's talk, this was related to this funny minus 1 to the power gamma prime that appeared in his Lie algebra. So what is this thing? So this sigma is just something that maps H1 of sigma use sigma for two different things. Oh, this is gamma. Sigma taking gamma to z2 plus or minus 1. I do not want to define it, but I'll tell you some property that it has. It has the property that sigma of gamma is plus 1 if there's a saddle connection with charge gamma, and it's minus 1 if there's a closed trajectory with charge gamma. Okay, this thing isn't a big deal. I mean, it's very annoying that somehow, when first encountered with this story, you shouldn't worry too much about this time. Okay. So now, okay, so you define this crazy automorphism for every gamma. And now...
and if there is no saddle connection for this gamma, what would you do?
So I said I didn't want to define it, I just wanted to describe some properties that it has. These are the only properties that I'm going to use.
Did you say homomorphism?
It is not a homomorphism. It is a quadratic refinement of the intersection pairing. Okay, so let me tell you one more property that it has, which together with this would suffice to determine it. And now what won't be obvious is that there exists such a thing, but nevertheless, let me... so it has the property that sigma of gamma prime is... So this would have been a homomorphism, but it's not that. It's minus 1 to the... It differs by this sign, minus 1 to the pairing of gamma.
Is canonical sigma gamma?
In this, yes,
This
there's a canonical thing with these properties. It's related to the fact that there's a canonical spin structure on the spectrum curve. Yes. Okay. So now we're supposed to. Let me just slightly restate Maxime's rule. So we're supposed to draw a picture. So I draw a picture. So this picture, the vertical axis is going to be my theta, the parameter that we were calling theta. And the horizontal axis, really this should be the whole parameter space of quadratic differentials, what I call B over there. But since I only have one dimension, just think of some path, some path in B, some real path parameterized by C. So now on this picture, I'm supposed to put a bunch of curves. So I'm going to put a curve for every special trajectory. So at this point, for example, there's some collection of special trajectories, and they're going to correspond to various curves passing through this point. So since the special trajectory also persists for nearby values of the parameters, it makes some curve here. So the location of the curve is just where you think it should be. So if the curve is labeled by a charge, say gamma, so this trajectory I call L gamma is just the locus where e to the minus I theta z gamma is real and negative. In other words, sitting at this fixed quadratic differential, I sweep through the phases, I vary the phases, and I look at the moments where I see closed trajectories. Now, the moments where I see special trajectories. Now I'm just making a picture of that as I vary. So this is some omega. You could draw all of them, but for convenience, let's only draw the ones with omega not equal to 0. So only draw the things where some special trajectory actually occurs. So then, since I've got several special trajectories, generically I'll have several of these things, and the places where they cross are exactly the places where the walls are. Right? This is exactly where two of these z gammas have become aligned. And so at those places, we know, at least from the examples, we know that it's possible that some new ones will be born or disappear. So the picture looks something like this. There might be more than, well, we saw in one example, infinitely many things were born, so it might be more complicated. But so you have some picture like this. So maybe, some other wall crossing is happening down here, maybe. There could be some other ones that don't interact with, let's not draw that one, that'll make it annoying. Maybe, oh yeah, no, it's all right, it's all So some picture like that. And now you're supposed to consider, well, you consider actually any loop on this picture. Sort of formally speaking, any loop. Let me just speak formally for a second. Well, let me first consider, well, no, let's consider the most interesting loop. So look at this loop here. Or actually, let me draw it square. So you consider this little loop. So what the Kontsevich-Soyleman formula says is that as you travel along this loop, say from this point to this point, so you do the following thing. You take a product of these automorphisms. So as I go along this trajectory, every time I meet one of these walls, I take the corresponding automorphism. So this one was some omega, so I take the automorphism k gamma to the power omega of gamma at this moment. Then here, this one's labeled by some gamma prime, but I take the automorphism k gamma prime to the omega of gamma prime. And so on. I just travel along this path, taking the product of all the automorphisms that I need. And then having done that, I arrive at this final point. So that gives me some composite automorphism, some complicated automorphism of this algebra. But then I could also do it the other way, so I could have gone here first and then gone down. And then I would meet a priori a quite different looking product, right? It has these automorphisms. First of all, they're occurring in a different order, right? This one, I now meet gamma prime before gamma, and second of all, I also meet all these other ones, the new invariants that were generated at this wall crossing. And the statement of the wall crossing formula is that the two products of automorphisms that you get going this way and going this way should actually be the same. So let me write that. So let's see, use Maxime's notation. So if I call this theta, and this theta prime, I could define A of this pair of phases, theta and theta prime, to be just the product over all gammas with argument of z gamma lying between theta and theta prime of k gamma to the omega gamma, taken in order of increasing phase. So this is A of theta, theta prime, and u. It depends on where I am here. And the statement is that in this situation where there's nothing that goes out like this, which Maxime also had this condition, in that situation, these two products should be the same. So A of u should be just equal to A of u prime. So this is u, and this is u prime. But another way of thinking about this, which is going to be useful for us later, is to think of this as a kind of flatness condition. You know, you could equally well say that when I go around this closed loop and I come back to the original point, if I take these automorphisms, but now take them with a sign, remembering which way I crossed. So here I get the automorphism, here I get the inverse automorphism. Then you could say that the product of things together on a closed loop is 1. At least formally. Now there's some problem. If you actually try to implement that in the case of these infinite products, you may get some headaches about conversions, and then it's better to say it the way Maxime said it. But sort of formally, this is the picture. It's just a kind of flatness. So this is the wall crossing formula. And so let's see how it works out in these two examples over here. So say in this example, this example would correspond to this simple picture, where I just have gamma 1 and gamma 2 on one side. And on the other side, I have gamma 2, gamma 1 plus gamma 2, and gamma 1. And so what the wall crossing formula here would say is just that k gamma 1, k gamma 2, which is what I meet by going this way, is equal to what I meet by going this way, k gamma 2, k gamma 1 plus gamma 2, k gamma 1. So this, I remind you, was in the case where the inner product of gamma 1 with gamma 2 equals to 1. And so this, so Maxime also said it, I'm just re-saying it. But this you can really check. This is an easy exercise, which is fun to do. You have the actual formula for those automorphisms there. Nothing is hidden from you, you can just check it. Okay. So, but I guess the other important thing to say is that this identity, moreover, determined, the right side was determined in terms of the left side. So, if I ask for a product of, some product of these k factors, these automorphisms, to be done in the order of the potential charges on this side, with some arbitrary omegas appearing, the only solution will be exactly this. That's the unique factorization that Maxime accomplished. So it really determines the stuff on this side from the stuff on this side. Okay. So again, you might say that's not so exciting, just two things turned into three things. But what's cooler is that it also works here. So this is now the example of two things turning into infinitely many things. So the phases are accumulating. So this n gamma 1 plus n plus 1 gamma 2, its phase is getting closer and closer to a sort of critical phase, which is the phase of gamma 1 plus gamma 2. And then, sorry, that's a terrible picture. They're accumulating in the middle here. And this also corresponds to a sort of wall crossing. This also corresponds to an identity among simplex morphisms, which was written down also by, well, maybe they didn't write down exactly this, but Conceivable Soberman wrote down something very close to this. Something from which this can be trivially produced. But I can never write it without. So now on this side you just have two things, and on the other side you have some terrible infinite product. Product n equals 1 to infinity of k, n plus 1 gamma 2 plus n gamma 1 times, now some special guy in the middle, k gamma 1 plus gamma 2 to the power of minus 2, that one corresponded to the saddle connection, and then times another product going the other way from infinity to 1. These things don't commute with each other, so it's important to keep track of the order. Well, otherwise the whole wall crossing formula would be trivial.
No, I think it goes from 0 to infinity.
Yeah, 0, thank you. Yes, it's right. I want the gamma 1 and gamma 2 to still be there on the other side. Yeah, thank you. That's right. So this is a much more complicated identity among again, these automorphisms. So it's an identity among concrete objects. Here to really define it, you have to think a little bit about what it means to take this infinite product, but it's defined by some kind of truncation, as Maxime explained. And this, again, it's not so easy to prove it. It's not so easy to prove it, but you can check it. You can check it on a computer and see that it's really true up to any finite order. And that's also a kind of fun exercise. It takes a little longer.
Do you understand properly that this goes the other way around? In the sense that these identities were independent of every quadratic differential and Riemann surface. It's just some identities algebraic.
Yes.
Absolutely, absolutely. So that's the cool thing about it, is it's this amazing algebraic identity, which, imagine I didn't know anything about quadratic differentials.
It's a way of proving that.
No, in fact, the origin I first discovered by computer.
Oh, you discovered, but not by studying quadratic differentials.
No,
by,
just symbols here.
Yeah. Okay, great. So it can be checked by computer, and in fact, it can be discovered by computer. But yeah, that's right. This is just an algebraic identity in some group of simplex morphisms, group of automorphisms of this algebra. A priori has nothing to do with quadratic differentials, but miraculously, it is the answer to this question involving quadratic differentials. Right? Even this crazy structure of an infinite tower of, infinite set of saddle connections plus one special closed curve, all of that just appears automatically somehow from these algebraic things. That's what's kind of cool about it.
So anytime you know bifurcation, you get a formula for free.
Anytime you
get a bifurcation of quadratic differential.
Okay, I see.
Understand what is the situation.
So that's true. So I could, in principle, do this backwards. I could sort of prove this formula by studying the quadratic differentials. I think that's right. You could prove this formula by studying the quadratic differentials. As it turns out, in this case, you won't get many more formulas. I think by studying quadratic differentials, basically you only get the two formulas that I already wrote. But I'll show a generalization later, which may lead to more stuff. Anyway, this example is already pretty interesting. It suggests that there's some structure here that needs to be understood, right? Why do the quadratic differentials obey this crazy formula?
And do you have also, if the intersection is 3, we'll have two asymptotic rays or something like that? Yeah?
If the intersection is 3, it's a much more complicated story. So in that case, so I haven't studied it myself, but it's been studied by Gross and Pandey and Siebert in a sort of different but related context. And my understanding, okay, maybe Maxime knows better. My understanding is that in that case you get rays which are actually dense, not only
dense in some subsector.
Yeah, in some subsector. That's right. So the picture is somehow like, so the boundaries of the thing are here. then you have some walls that kind of accumulate. Sorry. Then you have some things that accumulate, but the place that they accumulate at from the two sides is not the same place. So they accumulate down here, let's say this one, and then there's this crazy region in the middle where they're just dense. And I believe that no one has written a closed formula for what the...
No, but for central rays, we know the answer.
For the central ray, it's known. So it's known what are the invariants that occur exactly on this one. It's not just a single invariant, because you also have all the multiples of the charge. So there's sort of a countable set of invariants that are supported here, and those are known. But I think for the generic rays, I think it's not even known what they are. So it's funny. So it's a simple algebraic question. You just multiply these things, compose them in the other order, and see what you get. But
Yeah, even the growth of omegas is not really understood here.
okay, even the growth.
Yeah.
So fortunately, that situation will not occur for the quadratic differentials. And it probably will not occur even for the generalizations I'm going to talk about. But it does occur in some more fancier context.
So why doesn't because you only have two ends essentially?
Essentially, yeah. I mean, yeah. Now you might say, what about the closed ones? Can't they somehow intersect in some more complicated way? But I think it just never happens.
I mean, so is the density here somehow quality different to the density that I would have if I had a holomorphic quadratic differential? Is it not somehow filtered by things that are not dense in the mass or something?
I think it is. I mean,
No, it's so
Right.
the charges are getting bigger and bigger.
Right. So somehow, why is this worse than what? I mean, you said that we would expect things to be fine if we had holomorphic quadratic differentials, although the walls would again be sort of dense.
Right. No, I didn't exactly say that it's worse. I just said that I don't understand. I don't know what the formula is in this situation.
Right.
They're dense, so it's bad in some psychological way. I mean, since this doesn't actually happen for the quadratic differentials, I don't know how to.
But maybe I don't know.
omegas grows too fast in a sense.
I see.
Oh, that's true. If they grow too fast, then it would be a problem. Yeah,
Right.
maybe.
Right. Okay. so-
But perhaps one way how it can appear for quadratic differentials if you would count not only those lines but also those tripods with 180
For
degrees.
SU3, no, I don't think
No?
it's.
Those tripods will occur not for quadratic differentials, but for higher rank.
But you cannot. Right. Yeah, I see. Okay.
Yeah, there's no tripods for foliation. There's just leaves of the
Of course,
foliation. They can never hit each other.
Right.
But yeah, we'll come to that. We'll come to that.
Can you prove down to earth for holomorphic quadratic differential what's dense, which can never be dense in the presence of a pole? I didn't get that statement.
Yeah, the statement is that for a holomorphic. Sorry, let me think about how to say it. Well, one thing that can be dense without the pole is just a single trajectory. So you just look at a particular trajectory of the quadratic differential.
Okay.
Say one of these S walls. It can actually be dense on the whole curve. Just a single trajectory.
Okay.
Which doesn't happen in the presence of the pole, roughly because once it gets too close to the pole, it falls in.
Yes.
And so that makes the whole structure a lot simpler because you can imagine if you're looking for places where two trajectories hit each other, and the trajectories are themselves dense on the curve, then they're going to hit each other quite a lot. So the phases at which, I guess I'm saying that the phases at which saddle connections occur could probably be dense in the circle
True.
in the presence of.
I mean,
They
holomorphically,
always
they
are.
always are.
Yes.
And in this case, it's always a closed countable set.
Great. That
So
That density is okay.
right. So they can accumulate, but they can't be dense in the presence of the poles. Yeah. Thanks. Sorry, that was very good to say. Great. Okay. So I want to start. I want to try to explain why this formula is true. Having introduced this bizarre structure. I think Maxime will have quite a different way of explaining why it's true, but I want to explain sort of the way we found thinking why it's true. Okay. So, now, as I said, the way I'm going to explain it is a little bit work in progress. So this is a new way we have of thinking about it. So there's some probability of error, but the basic construction is already clear. It seems to be something really something that's somehow basic to the structure. So y is KSW of true for our omega gamma. And the way we're going to see it is by introducing a sort of funny-looking new construction. So it's a new thing that you can do with a quadratic differential. So given a quadratic differential, I'm going to define something that I'll call a path-lifting rule. Sorry, not just given the quadratic differential. Given the quadratic differential and a particular phase, I'm going to define something that I'll call a path-lifting rule. So let's recall. Let's recall the two things that we're going to need. On the one hand, we have this double cover, the spectral cover, by the 2 square roots of phi2, so double cover sigma over c. And on the other hand, the S-walls. So those are somehow the only 2 data which will go into this construction.
Can I ask a question? Do you equip the double cover with a choice of the square root of the lift? Or you don't need?
The double cover is, by definition, the double cover is the Riemann surface of that lift.
So by definition, Q star of phi is lambda tensor lambda. But it's also minus lambda tensor minus lambda.
I define it in the following way. This double cover is this subset inside of cotangent of C. So defined in that way, I think it comes with a canonical choice of the lift. Namely, a point of that thing is a choice of the lift. So yeah, that's the so we have that, and we have the S-walls, which, let me remind you, now I'm in a generic theta. I'm going to be in a generic theta. So the S-walls, I'm not talking about special trajectories. I'm just talking about these 3 things that come out of every. So theta is going to be generic. So what is this rule? So it's going to be a rule where I take any path on C and I lift it up to a path on sigma, or more precisely, not just a single path, but a linear combination of paths. So actually, I want to leave this algebra here. So we have this funny algebra here, which had something to do with closed paths. The meaning of it is not quite clear, but at least it had something to do with taking linear combinations of closed paths on sigma. And so the way we're going to explain it is actually to do something involving open paths. So for every open path, meaning a map of the interval into C, I'm going to define L of P. Really, it's L of P, theta, and phi 2, but I'll mostly suppress these and just call it L of P. L of P, and what it's going to be is a z-linear combination of open paths on sigma. And it's going to have 2 important properties. So the first property is going to be a kind of composition property. So L of P prime. So given 2 paths P and P prime that have a common endpoint, so if I have path P and P prime, I can concatenate them. As long as they have a common endpoint, I can concatenate them and make P prime. And this path lifting rule is going to be kind of compatible with that structure. So L of P prime is going to be L of P times L of P prime. So that's going to be one thing. And the second thing is that the rule is going to have a kind of homotopy invariance to it. So it's only going to depend on, it's not going to depend on the actual path, but it's only going to depend on the homotopy class of the path. Okay, to be honest, I'm hiding that little minus sign here. So there's going to be a kind of twisted homotopy invariance. I'll explain what twisted means when the time comes. But basically, it's homotopy invariance. And then if you think about it, this should sound a little weird because if you think about having a path on the curve and you try to lift it up, usually you would think what you get will depend a lot on the homotopy, because if you homotope it past a branch point, it should suddenly move to the other sheet. So somehow this construction has to deal with that problem. It has to manage to be homotopy invariant even when you move across a branch point. So that's sort of all the subtlety in the story. So let's get over there. So let me start by saying what I do for paths that are kind of short. And what I mean by short is that they don't cross any of my S-walls. Yeah, the S-walls are still there. So remember, we've got a curve decorated with this structure of S-walls. So if P is short, in other words, it doesn't meet any S-walls. Well, then I'll do just the only obvious thing you could think of doing. Namely, I take I just lift it up to the sum of the two lifts. So here's P. So I have my double cover here. And there's no branch points. It's not coming too close to the branch points because the branch points have S-walls coming out of them. So if it doesn't need any S-walls, I can sort of forget the branch points for the moment. So I just have two sheets, call them sheet 1 and sheet 2. So I lift it up to P1 and P2, just the two preimages. It's an oriented path. So I lift it up to its two preimages here. So L of P will just equal P1 plus P2, a sort of formal linear combination. And now, of course, if I have two little short paths, suppose I also have P prime. Here's P1, here's P2. If I have another little short path, then here I have P prime 1 and P prime 2. And so I want to say that this has my sort of composition property. Well, what does it mean? So this is supposed to equal L of P times L of P prime. Well, what it means is, so here I've got P1 plus P2, P1 plus P2 times P prime 1 plus P prime 2. So here I've got P1, P prime 1, sorry, P1, P prime 1, P2, P prime 2, and then a priori I have two more terms, but those two other terms correspond to sort of non-composable combinations of paths, right? It's like trying to compose this one with that one, or this one with that one, and those terms I just declared to be 0. Okay, so we've got some multiplication rule for paths upstairs, and the product of two non-composable paths is just 0. So with that convention, then this rule obeys the obvious property obeys, obviously, this property. Now, if I just stopped here, if I just did this for every path, of course it would totally fail to be homotopy invariant. It would depend drastically on which way you go around a branch point. So how am I going to make it homotopy invariant? Well, I'm going to do something different when it hits an S-wall.
When you speak about homotopy of open paths,
Homotopy of open paths, yeah.
in
Fixed ends?
Yeah, with fixed ends, exactly, with fixed ends. So yeah, so what we're worried about is, for example, this situation, where I have a branch point here. Where I have a branch point here, and I have two paths, two paths like this. So far, my rule would be very non-homotopy invariant. The lift of this one would look quite different from the lift of this one. So I have to somehow deal with that problem. So how do we do it? Right. So because of this sort of composition property, I really only have to tell you what happens when I cross one S-wall. And then if it crosses multiple S-walls, I'll just build it up by composition. So what happens when the path crosses one S-wall? So now the picture is, here's my path P, here's an S-wall. It came out of some branch point, but that branch point might be very far away. It might be closer, it might be far away. If P crosses one S-wall like this, then L of P is going to be the sum. So before I had two terms, just a lifts to either sheet. Now I'm going to have three terms. So two of them are just like before. Two of them are just like before. I can lift this thing up to sheet 1, or I can lift it up to sheet 2. And the third thing I'm going to allow is something where the path, I have to first show it with my finger and then try to figure out a notation for it. So what it does is, the path travels along one of the sheets. Let's say, let me try to write the 3 lifts. Sorry. P1 plus P2 plus something else. So I'm going to write pictures of the 3 lifts. So the first 3 lifts here. So 1, 2, 3. So I'll represent them just by putting the number of them. So the first one is just width to sheet 1. The second one is just width to sheet 2. These are P1 plus P2. And the third one is going to be a path which starts out on one sheet, but then takes a detour to the other sheet. How can it get to the other sheet? Well, the way it gets to the other sheet is to go down the S wall to where the branch point is. Then it can come back on the other sheet. So it's going to be like this. Goes down like that. Comes back. So it's on, say, sheet 1 here. It travels down sheet 1, comes back on sheet 2, like this. So it's a little tricky to give a notation for this one, but let's write it. If I divide the original path into sort of P plus and P minus, then what this one is P plus 1, P minus 2, and then in the middle there's a path associated with the S wall, which I'll just write as S. I'll write it as S1, 2. Now you might say, how come it went from 1 to 2 and not from 2 to 1? That's determined by the orientation of this S wall. So the S wall, when it's lifted up to the cover, actually has a natural orientation given by the 1 form there. And so the rule is that this thing is only allowed to go, I think, when it is opposed to the orientation of the S wall. Anyway, there's some definite rule that fixes one or the other. So this is going to be my thing. So now I've changed